Hello. Good afternoon, everyone. My name is Apostolos, and today I'm going to talk about a recent work on evaluating aggregation-based location privacy, a joint work with Carmela Trongoso from India Software and Emiliano De Cristofaro from University College London. Our motivation is slightly different than the previous work. Specifically, in this work, we work with aggregate locations, and aggregate locations are useful for training various machine learning models to perform all sorts of mobility analytics in the context of a smart city. For example, there are various applications that we can predict traffic volumes in a smart city or detect some events and some anomalies that could be useful for traffic provisioning. And because we're talking about aggregate locations, this is often considered as a privacy-friendly approach, especially because we know a lot of good protocols out there that you can have an oblivious aggregator who can collect the aggregates in a privacy-preserving way, meaning that he can learn only how many people are in specific locations, but not which people specifically. However, we identified an open problem that there is no sound methodology to reason about privacy leakage from the aggregates about individual users. And to this end, there is also not a way to evaluate potential defense mechanisms that can protect us against this kind of leakage. So in this work, we do a first step to address this gap. And we propose a framework that can allow us to reason about privacy laws for individual users from aggregate location time series. And we do an experimental evaluation on 2 real-world mobility datasets, one coming from the Transportation for London Authority and one from the San Francisco Cab Network. Furthermore, we use a framework to evaluate the privacy protection that we get from defense mechanisms, and since we are talking about aggregates, differential privacy is a suitable defense mechanism, and we specifically study output and input perturbation techniques. Our experimental results show that the raw aggregates actually do leak information about user location and their mobility profiles, and that differential privacy can provide a strong privacy protection when actually the utility of the aggregates is poor. I will jump into the description of our framework. We introduce an adversary that has some prior knowledge about the users. Now, this prior knowledge in practice can originate from various sources, from social networks, data leaks, location traces released by providers, or even personal knowledge. For example, I might know where a user lives and works. And for the sake of this work, we explore several possible approaches to generate this prior knowledge. In particular, we focus on 2 categories. We have the probabilistic prior knowledge, which can be generated by taking into account the frequency of locations that the user visits or the seasonality of visits for a specific location, and this seasonality can be over a day or a specific time of the day or over a day of the week. Moreover, we have the assignment prior knowledge, which can be created taking into account the user's most popular location or all the locations that he has visited at a specific period, or even we can follow some sliding window approach that take into account the locations that the user visits during the last epochs. And this epoch can be the last hour, the last day, or even the locations that he visited the last week. So we introduce some inference strategies in our framework, which work on input the prior knowledge about the user and the aggregate location time series. And the first one is a Bayesian updating that we attempt to estimate the posterior probability of a user being at a specific location at a specific time slot, given the prior knowledge that we have about him and the released aggregates. And then we propose also 2 greedy strategies that take into account some characteristics of datasets. For example, the max ROI strategy assigns the most likely users to a location, and this is sort of like assuming that the same users visit the same locations. Or we can follow another greedy strategy that assigns the users to their most likely location until all the aggregates are consumed, meaning that the users are going to be visiting the same locations. The timeline of our framework is that Similar to a machine learning approach where you have training and testing data, we have the observation period during which we build prior knowledge for the users, and we have the inference period over which we launch the attacks and we try to infer information about the locations of our users. The goals of the adversary are twofold. The first one is user profiling, and basically he's trying to infer the probability of a user being at a specific location at a specific time slot. And to reason about privacy, we want to measure adversarial error. And since we do profiling, the inferred profile is a probability distribution, and we have the ground truth. And to capture this adversarial error, we take the Jensen-Shannon divergence. Also, we consider user localization, where the adversary actually tries to predict the actual locations that a user is likely to appear. And to evaluate the adversarial performance, we consider his precision and his recall, similar to a classification task. And to capture adversarial error, we use 1 minus the F1 score. So the lower the F1 score, the higher the adversarial error. In any case, for both of the adversarial goals, we measure the privacy loss as the normalized reduction in adversarial error with and without versus without the aggregates. In particular, we actually measure how the adversary reduces his adversarial error as he's given the aggregates. First, now I'm going to present some experimental results on that we did in a paper, and we actually evaluate row aggregates. I'm going to talk a bit about the datasets that we used. We have the transport for load dataset. It contains 60 million trips performed by 4 million Oyster cards, and these trips are distributed over 582 stations or regions of interest in the wide area of London. It's a dataset back in 2010 and contains 4 weeks of data. It's a relatively big dataset, so we sample the top 10,000 users per total number of trips that they perform, and we observe that this dataset is relatively sparse. The users don't report so much location because the signal is actually coming from commuters who tap in at the station with their card or tap out at the station. Second, we use the San Francisco CAP dataset. It contains 11 million GPS coordinates generated by 534 cabs in San Francisco back in 2008. We split the San Francisco area to a 10 by 10 grid with this specific size. This is a much denser data set compared to the TFL1, where we see that the taxis report on average more than 3.5K locations. It's a very dense data set and a very irregular one, as the taxis move around all the time. To build prior knowledge for the users, we split data according to time. Specifically, we use the first couple of weeks to extract prior knowledge, and our inference period is the last week of each data set. So in terms of user profiling, when the adversary has as his prior knowledge the location frequency of the users over the observation period, we do some experiments on the TFL. This is, we see these results. This is a CDF over the oyster population, which plots what is the probability of the adversary having a specific value of error. The blue line is his performance when he uses only the prior knowledge about the users, whereas the black, red, and cyan lines are his improvement when he's using the aggregates and specifically the attacks that we described before. We see a significant improvement, and the area between the prior and the output of our attacks is actually the privacy loss that the user loses from the aggregates. Similarly, for the San Francisco CAP dataset, we see that 2 of our attacks improve the adversarial prior knowledge, whereas the attack that we assumed ROI regularity of location is not working that well, probably because the same camps do not visit the same locations. Putting the 2 data sets side by side, we observe that inferring the mobility profiles of commuters, it's much easier than inferring the profiles of cabs, who are highly entropic. And also, we observe that the users of the commuters are highly regular. This regularity motivates us to do some further analysis and on how these regular mobility patterns affect privacy. So we did an experiment that we consider as prior knowledge the location frequency for time instances of any day. And this is a graph that plots the adversarial error over the inference period. So it's over the 1 week that we try to profile our users. So what we observe is that in the morning peak hours, the aggregates do not help the adversary so much compared to the midday or the evening hours. And that means that the users are likely regular in the morning hours because they commute to work. So the aggregates, the prior knowledge has already what I need to know. Whereas in the midday or the evening hours, we see that the aggregates actually help the adversary to better profile the users. And we see a similar pattern on the weekends where the users are likely to follow variable routes for entertainment. In terms of user localization, when we consider as prior knowledge the location frequency for the time instances of a week, we see some similar results. When we consider as our baseline all the locations of the prior, we see that the Bayesian strategy doesn't improve a lot, but the greedy strategies actually help the adversary localize the users on the TFL dataset. And similarly, on the SFC dataset, we see that when we consider the most popular locations of the users, the adversarial error is getting very high, but still our greedy strategies actually yield some privacy loss for the cabs. When we test, when we experiment with various kinds of prior knowledge, we see that the commuters are best localized by the most popular locations, whereas cabs by the locations that they visit during the last hour, probably because they drive back through the same locations to the place that they started their trip. The takeaways of our analysis is that the aggregate locations actually help the adversary to profile and localize users, and the degree of privacy loss is actually highly dependent on the prior knowledge that we give to the adversary. We find that the assignment priors yield smaller privacy leakage, and that is because these kind of priors are already very informative compared to probabilistic ones. So next, we now have a framework to quantify privacy loss from the aggregate, so we can use this kind of framework to evaluate potential defenses. Since we are talking about aggregate locations, which means like basically count queries, this is a suitable setting for differential privacy to bound the privacy leakage. Specifically, we said to experiment with differential privacy and evaluate how much privacy we get when we do this perturbation, of course, with respect to the parameter epsilon and the resulting utility of the aggregates. We define privacy gain as the normalized increase in adversarial error when we are given the differential privacy aggregates compared to that with the raw aggregates. And for utility, we consider the mean relative error of the aggregates over all the locations in the data. First, we focus on output perturbation techniques, where you have an aggregator who is going to add some noise to the aggregates before he releases them to an analyst. We focus on the simple counter mechanism, which is a straightforward application of the Laplace mechanism to location time series. And this kind of mechanism provides event-level privacy guarantees. So we are protected in a specific location at a specific time slot. And of course, we can configure the amount of noise that we add to get stronger privacy guarantees, for example, epsilon differential privacy. We also study the Fourier perturbation algorithm, which improves the privacy utility trade-off by reducing the amount of noise required, and specifically the noise addition is happening on the frequency domain, and this provides epsilon differential privacy at the time series level. When we evaluate the privacy that we get out of the privacy gain that we have, we see that with increasing epsilon parameter, the privacy gain naturally decreases, especially for those mechanisms that are not supposed to provide strong privacy guarantees, like the simple counter mechanism with epsilon provide event-level privacy, and the Fourier perturbation algorithm provides epsilon privacy per time series, whereas the stronger mechanisms who provide epsilon differential privacy overall keep the privacy gain relatively high. But this comes at a high cost in the resulting utility of the aggregates. We observe that as the epsilon parameter increases, the the utility is getting lower, so the mean relative error decreases, so the utility is getting better. But if we rank the mechanisms from bottom to top, we see that as the privacy guarantees get stronger, the utility is getting worse and worse. We also study input perturbation mechanisms based on randomized response. So the users perturb the inputs before they communicate the locations to the aggregator. There is the spot me mechanism, which users report to be in a location with some probability, or they report the truth with probability 1 minus p, and this p is a parameter of the algorithm. The aggregator collects the perturbed inputs and estimates the aggregates. In terms of privacy for these techniques, we see that as the p parameter increases, we have the privacy gain increases, and this is significant in the sparse TFL dataset, but on the dense SFC dataset, the privacy gain does not increase so much. In terms of utility, we see that the mechanism overall provides slightly better utility than an output perturbation mechanism, but still we see with increasing p-value the mean relative error increases. In conclusion, in this work we present a framework that allows us to reason about individual user privacy laws from the release of aggregate location time series. Our experimental study shows that location aggregates actually enable an adversary who has some prior knowledge about the users to profile them and localize them. We also find that differential privacy mechanisms improve privacy, but this comes with a high cost in the utility of the resulting time series. And to this end, we believe we need some novel defense mechanisms that enable us to do privacy-friendly mobility analytics over aggregate locations. Thank you very much, and I would be happy to discuss anything you